I'm going to solve quiz 2 of unit 8 that says like this. A proton moving with velocity v equal to 1 times 10 to the 6 meters over second enters a region with a magnitude field v vector equal to minus 0.5 t. So here we will have our magnetic field v equal to 0.5 t, and it's minus 5 because it's going downwards. In z, the velocity vector is at an angle of 60 degrees, so with respect to the positive z-axis. So here we have our z-axis, so our z-axis, and here we have y. So here we have our 60 degrees. First we have to analyze the motion of the proton and describe its trajectory, and make a sketch and describe it in words as clear and detailed as possible, and if you were explaining it to Peppo. So first we noticed here that here we have our velocity vector that is moving 60 degrees according to the z-axis. So here we will have two types of velocity: the parallel velocity and the perpendicular velocity. The perpendicular velocity will be according to the z-axis, so we will have that the perpendicular velocity will be equal to our velocity that it was given to us with the value of 1 times 10 to the 6 meters over second, and this, as it is parallel, will be equal to the cosine of 60 degrees, and our perpendicular velocity will be equal to our velocity times our sine of 60 degrees. Okay, once we know this, we can describe the motion of the proton, and when the proton enters the magnetic field, the velocity parallel to the z is not affected because it's constant, but the perpendicular velocity will be affected by the magnetic field because it's not entering according to the magnetic field. So it will be affected by the magnetic field, and it will start to oscillate in the shape of helices. So that is the answer for the first part of the problem. Then for the second part of the problem says that we have to find the radius r of the trajectory as seen from a plane perpendicular to the magnetic field. Okay, so for B we will have to consider our formula that the force of the magnetic field is equal to the charge of the velocity perpendicular cross product of our magnetic field. Okay, and all of this is vectors. So as we can see, this will be this is not only the perpendicular, is for both. So here we can notice that here we will have the charge times the velocity of the parallel plus vector plus the velocity of the perpendicular times cross product the magnetic field. And once we have this, we can divide this into two parts. First for the parallel part, and the parallel part is the charge times our parallel velocity cross product our magnetic field, and this plus our charge plus our perpendicular velocity cross product our magnetic field. And this part, as we said, it was a constant when it was entering the magnetic field, because it enters according to the direction of the magnetic field. So this will be equal to 0. So we are only left with this part, the perpendicular part. So the perpendicular part, we have to obtain the magnitude of our force. So the magnitude of our force will be equal to the cross product. It will be equal to the charge times the velocity of the perpendicular times the magnetic field. Okay, and then if we want to make it circular, because it's circular, we can consider the centripetal force, that it's equal to m, the mass, times our velocity square over our radius. And if we can see, we can this part goes in here, because we want to calculate the radius. So if we want to calculate the radius, this part goes in here, this part goes in here, and one of the velocities cancels with one of the velocities, and then we are left with the mass times the velocity, here only one, and the charge goes down, and the magnetic field also goes down. Okay, so this is the formula for the radius, and then we only have to substitute, but we know that the perpendicular velocity is equal to the velocity times the sine of 60. So the mass, we are going to determine the mass of the electron, and the mass of the electron is 1.667, times 10 to the minus 27, and this times our velocity, that is 1 times 10 to the 6th, and this times the sine of 60, because we said that it was the perpendicular part, over our charge, that we have to consider the charge of the electron, of the proton, that is 1.6 times 10 to the minus 19, and our magnetic field, that is 0.5. So times 0.5. And once we make this operation, we will obtain that the radius is equal to 18.08 millimeters. And this is for part B. For part C, I'm going to do it here. We are asked to obtain the period t and the frequency of the motion of the plane. So we are going to obtain first the period, that is 2 pi over the angular velocity, and this is equal to 2 times p pi, but the angular velocity is equal to the radius over our velocity. But we are working with our perpendicular velocity, so this is equal to 2 times pi, but we know that our radius is this part. So this is m times our velocity over the charge. So here we cancel the velocity, and we are left only with 2 pi times the m over q times v. And this is equal to 1.312 times 10 to the minus 7 seconds. Okay, so this is for part C. And for obtaining the frequency is 1 over the period. So it's only 1 over 1.312 times 10 to the minus 7. Then this is equal to 7.64 times 10 to the 6 hertz. Okay? And for part D, we are asked to obtain the distance covered by the proton along the magnetic field direction. And this is equal, the distance is equal to the velocity, but we are using now the parallel velocity because it said that it's covered by the proton along the magnetic field. So we're not using the velocity that it's perpendicular to the magnetic field. We are using along the magnetic field. That's why we're using this parallel. And this is times our time. And so the time, this is equal to this times the cosine of 60 because we set it there, and the time is equal to the period, that is 1.312 times 10 to the minus 7. So our distance is equal to 0.0656 meters because we know the velocity and we know this part. And this is how you solve this problem.